Hi everyone, welcome back. Let's go back through the lecture on first order linear systems, and we're going to go give a couple more examples as well as more detail on how these derivations work. So first, let's remind ourselves from differential equations. Well, we know that any kth order ODE can be converted into a system of k first order ODEs. Let's see an example of this just so that we're all reminded of how that works. So let's do a pretty simple second order ODE. So let's say x double dot plus 2x dot, let's say minus x, just so I don't, minus x is equal to t squared. Okay, so it's an inhomogeneous linear second order equation, ODE. So once we have that, well, we want some y variables that we're going to convert our thing into. So let's start by converting it into, let's say, y1 is equal to x. Let me make that an arrow. y1 is equal to x. Okay? So we're just going to rename our variable. You don't always have to do this, but sometimes it's nice. And let's say that y2 is equal to x dot. So these are our two variables. Well, you notice here that this is also equal to y1 dot. And so we can write this in just in terms of the y's, instead, so we can completely replace the x's. So when we do that, we end up with two first order ODEs. So we have y2 is equal to y1 dot. And of course, we need to substitute these things in. And so you'll notice that x double dot is equal to y1 double dot is equal to y2 dot. And so we also get y2 dot plus, let's see, what is x dot? Well, x dot is just y2 plus y2 minus y1 is equal to 0. And so now this is a system of two first order ODEs. And we can do the exact same thing with a kth order difference equation. So that's exactly what we've done in this section. So we start with, we're going to specialize down to the case where we have constant coefficients, just because that's a lot easier to work with. And so we do the same thing. And so we want to write our y variables as a vector, just because this will allow us to write it in matrix form later. And then we do basically the same thing, except instead of using dots, here we have t plus 1, or t plus 2, or t plus 3. So that's the sort of equivalent thing. So here we start off with y1 is equal to x. Here we start off with y1 is equal to x again. But then we have y2 is equal to x of t plus 1 instead of x dot. And of course, we can do the same sort of thing over here. And we get a system of k first order difference equations. And of course, this we need to write everything so that it doesn't make any reference to the x's, since we want a self-contained system. And so that ends up being these k minus 1 equations that are basically setting these new variables equal to x shifted in some amount. And of course, replacing into the original equation down here gives us our final first order difference equation. And we can rewrite all of that in matrix form. So you notice up here that, well, each of these is basically stating that y1 of t plus 1 is equal to y2 of t. And so that corresponds to, well, if we multiply this out, let's say that, let's imagine, let me use purple here. Let's imagine that we had, say, a y1 of t here, y2 of t through yk of t. Well, then when we're multiplying out, we multiply out this row and to the entire thing. And so you get that you have let me write this a little bit more clearly. So you get that y of t plus 1 is equal to, so the very first entry there is, let me write out the columns. The very first entry layer is y1 of t plus 1, y2 of t plus 1, etc. So that's equal to a times that. And so that t plus 1 term is equal to just y2. And so that's precisely this equation here. Okay, let me erase all that since it's written a little bit confusingly. And this final equation down here just corresponds to these coefficients down there when multiplied through. Okay, so now that we've done that, we have something that looks a lot like just a first order difference equation, except that all of our entries are vectors and matrices instead of just scalars. It turns out though that you can use many of the same techniques, and the principle of superposition still holds. So again, you can break up your problem solving into solving the homogeneous part first, and then the inhomogeneous, and then finding a particular solution to the inhomogeneous part, and then adding those together to get additional solutions to the inhomogeneous equation. And as in and in a particular case where you're dealing with a linear system of first order equations, you end up again getting a general solution that has k constants times k different linearly independent solutions to the homogeneous equation. Now, how do we solve for the homogeneous equation? Well, you can solve it by just setting it equal, and then we start with an ansatz, where an ansatz is just some assumption. So it's an educated guess about what form our linearly independent solutions are going to take. And so our guess is going to be that there's some solution that is where it's some constant vector multiplied by lambda to the t. And so that's our guess here. And our hope is that we can find k of these. That won't always be possible, but it turns out that it will often be possible. And given this ansatz, well, you'll quickly see that, well, you substitute the things in, and you get AV is equal to lambda v, which is precisely stating that lambda and v are an eigenpair of A, where lambda is an eigenvalue and v is an eigenvector. So the connection between this and what we did last lecture is that if you take a higher order difference equation, turn it into this sort of matrix form, then the roots of the characteristic equation are precisely the eigenvalues of A. If you take the determinant of our matrix A, you'll find that that equation is precisely the characteristic equation of the other form. And that has to basically do with the way we've created our companion matrix. Okay, so now that we've done that, where was I? So if we have k distinct eigenvectors, everything's hunky-dory, and you have k linearly independent eigenvectors, and so solutions of this form are linearly independent. Now, remember, when we had multiplicity of our characteristic root of the, root of the characteristic equation, then things went wrong, and sometimes you had things that were t to the n lambda to the t. So this part here. Here it's slightly more complicated because even if you don't have k distinct eigenvalues and you have multiplicity, you also have this additional v here, which allows you to get linear independence even when the eigenvalue is the same. And so you still will get solutions of this form, but it's not as clear-cut. You can't just measure it by just looking at the raw multiplicity, the number of times that the eigenvalue is repeated, because you also have to look at the linear independence of the eigenvectors. But using this procedure, you can again get k different linearly independent solutions and then combine them together. And of course, if things are complex, you'll often want to rewrite in real form, and so you use Euler's equation like you did last time to do the same thing and convert it into things that are shaped like that. Okay, so now once you have all of these, you can actually say a few more things, because as in the previous case, we can say things based on just the eigenvalues of our A matrix. And one of those things is, I think last time we talked about the strictly dominant eigenvalue. Here we're going to talk about a very similar concept. We're going to talk about the spectral radius of our matrix A. So if we have k different eigenvalues, then the spectral radius is just the modulus of the biggest one. So that's what this thing is saying here. It's just the modulus of the biggest eigenvalue. And so, of course, you can have multiple biggest eigenvalues. So this corresponds to the dominance of the eigenvalues that we talked about in the previous section. And one comparable theorem is that if you have a matrix that is a k by k matrix, and the spectral radius is less than 1, then that is true precisely if the limit as the limit as t goes to infinity of at is equal to 0. And I gave the proof earlier, but the basic idea is when you have these eigenvalues, if you are working in the case where you actually have k distinct ones, well, that's easy because you just write your vector as an eigen basis, or sorry, you do a diagonalization of your matrix, you take repeated exponentiations, repeated powers of each of your eigenvalues, or sorry, you take, and that sets the entire thing equal to 0 as t goes to infinity. It's slightly more complicated when A isn't diagonalizable, but it's still always triangularizable as a complex matrix, and you can do basically the same thing with a little bit extra work. But yeah, so that's a lot of theory. Let's spend a little bit more time and actually give an example or two to show you what this is like. So let's start by talking about, this is example 1.11. So in this particular case, we're going to first start by converting a second-order difference equation into a system of first-order difference equations. Let's start with x of t plus 2 minus 2x of t plus 1 plus x of t is equal to cosine of t. Well, what was our procedure for the conversion? We're going to let y1 of t be equal to x of t, and y2 of t be equal to x of t plus 1. Well then, we can also conclude that y2 of t plus 1 let's see, so that is, actually let me write this out. So this term here turns into y2 of t plus 1, and this term here turns into, what color am I? Okay. Oh, that's why. There should be a t plus 1 there, which is why I'm getting confusing myself. So this is minus 2y2 of t. And let's say that, well, that's easy. Let's just plus y1 of t. And let's just equal to cosine of t. And if we rewrite that slightly, we can get the system y2 of t is equal to x of t plus 1, and let's rewrite it in standard form. We get y2 of t plus 1. Oh, sorry, that's not the right one. That is equal to y1 of t plus 1. So if we rewrite that, we can get y1 of t plus 1 is equal to y2 of t, and y2 of t plus 1 is equal to minus y1 of t plus 2y2 of t plus cosine of t. Okay, and we can rewrite this in matrix form to get y of t plus 1. I keep on ending my parentheses without actually writing the 1. Is equal to ay of t plus b, where, of course, y of t is equal to y1 of t, y2 of t, and a is equal to 0, 1, minus 1, 2, because this here, let me actually write that out slightly differently. So this is 0, y1 of t plus y2 of t. So that's 0, 1, and this is minus 1, and that's minus 1, and that's 2. And b, this is, let's call this b of t, just to be consistent with my previous notation. B of t is equal to 0 cosine of t. Let's make all these square brackets. It doesn't really matter. But once you've done that, then this is now in a nice matrix form. And let's suppose that we want to figure out what the homogeneous solution is. So for the equivalent homogeneous equation, what do we have? So if we have the homogeneous equation, that's yh of t plus 1 is equal to ayh of t. And how do we solve this? Well, we have to do an eigen decomposition of A. So what are the eigenvalues and eigenvectors of A? Well, let's see. So in order to solve that, we have A minus lambda I is equal to 0. So and we want to take the determinant of that, which is equal to actually it's normally lambda I minus A, right? Let's do it that way. Lambda I minus A, which is equal to the determinant of, let's see, so that's lambda minus 1, 1, lambda minus 2, which is equal to lambda times lambda minus 2, and this is plus 1, which is equal to lambda squared minus 2 lambda plus 1 is equal to 0. And since that's equal to 0, this implies that you can factor this out. So this implies that lambda minus 1 is equal to squared is equal to 0. So lambda is equal to 1. So you only have one eigenvalue, and so this might be a problem. Let's try to compute the eigenvector of it. So let's say we had 0, 1, minus 1, 2 times, let's just say, call this y1, y2 is equal to y1, y2, which implies that, let's see, what is that? y2 is equal to y1, and minus y1 plus 2y2 is equal to y2. Plugging that in, you get that these things are equal, so y1 is equal to so that just means you just get y1 is equal to y2. So the eigenvector, there's only one degree of freedom. The eigenvector is just 1, 1. Or minus 1, or whatever. It's some c times 1, 1. But let's just use that as our eigenvector. So that means that we have some solution. Let's see, what would that be? That would be lambda to the t. But lambda here is 1, so one of our eigenvalue, or one of our solutions to our homogeneous equation is going to be lambda to the t times 1, 1, which is just equal to 1, 1. Okay, so that's one solution. So unfortunately, we only have one eigenvalue and one eigenvector, and so we can't actually get a second solution using just this method directly. Luckily, we chose a fairly simple example here, which we can solve using the techniques that we talked about in the last lecture. So note that the characteristic equation here, as a second order linear difference equation, is just lambda squared minus 2 lambda plus lambda is equal to 0, which implies that lambda is equal to 1 multiplicity 2. Which implies that 1 and t are linearly independent solutions to homogeneous equation. And so in this case, they're linearly independent solutions to a homogeneous equation. And so in this system, we can just plug that back in. So here we have this solution corresponds to the one solution, because of course we had here that y1 is just x of t. So if y1 is just x of t, and y2 is y1 x of t plus 1, then we can use that and plug that in to our other solution here. So, another solution using methods from last time is t, because we have the, where was that? y1 of t is just x of t, and x of t here is just t. And down here we have y2 of t is equal to y1 of t plus 1, or x of t plus 1. So that is, if you plug that in, then that's just t plus 1. And let's check this, just to make sure. So when we plug that in, then we get, what we have is t plus 1, t plus 2 is equal to, what was our matrix? 0, 1, minus 1, 2. 1, minus 1, 2. T plus 1. And if you multiply this out, well, that's t plus 1 as expected. And that here is, let me give myself a bit more space, minus t plus 2t plus 2, which is equal to t plus 1, t plus 2. So we couldn't have figured it out directly from just the eigenvalues and eigenvectors. Like I said, that gets a lot more complicated sometimes, and so we're not going to go into that detail. But for this particular case, we have a homogeneous solution, so let's call that YH. We have a general solution for the homogeneous solution, which is equal to C1 times 1, 1 plus C2 times t plus 1, t plus 2 for some C1, C2 in the reals. Okay, so now that we have a homogeneous solution, we could consider going back up here and looking to see if we can find the solution to the inhomogeneous equation. Unfortunately, these cosine of t's are really irritating, and they make life really hard. Because, unfortunately, when you're working with ordinary differential equations, you can easily take derivatives, and so dx dt, when you take the derivative of cosine, it's just minus sine. When you take the derivative of sine, it's just cosine. And so things work out nicely. Unfortunately, that is, I erased too much there. Unfortunately, that's not the case with difference equations, and so we're not actually going to take the time to solve the particular equation. But suffice it to say that if we weren't able to solve the particular equation, which is actually rather complicated here, you would then just add it to the homogeneous solution to get a general solution to your problem. And so that concludes this part of things. Let's see that again with a slightly easier example so that we can actually work through it a little bit more. And so this will be example 1.13, example 1.13 in the book. So let's start with x of t plus 1 is equal to ax of t. So we're just going to start with it in matrix form already, instead of having to convert it. So then a is equal to 2, 3, 2, 1. Where a is equal to 2, 3, 2, 1. And this is homogeneous, so we don't have to worry about particular solutions. Well, if we want to find the eigenvalues, well, again, let's take the determinant of lambda I minus a, which is equal to lambda minus 2, 3, 2, 1, determinant, lambda minus 1, which is equal to lambda minus 2 times lambda minus 1 minus 6, which is equal to lambda squared minus 3 lambda plus 2 minus 6, which is equal to lambda squared minus 3 lambda minus 4 is equal to 0. Minus 4, which we can factor into lambda minus 4 lambda plus 1 is equal to 0. So lambda is equal to 4 and let's write it the other way. Let's say minus 1 and 4. So since these are the, and we can also compute eigenvectors. So let's see. Let us actually compute the eigenvectors. So if we have the matrix 2, 3, 2, 1, so let's do this for lambda equal to minus 1 first, times, let's say this is x1, x2, is equal to minus x1 minus x2. That implies that we have 2x1 plus 3x2, 2x1 plus x2 is equal to minus x1 minus x2, which implies that 2x1 plus 3x2 is equal to minus x1, 3x1 is equal to minus 3x2, x1 is equal to minus x2, and so we have, let's call it lambda 1, and we have here that v1 is equal to, say, 1 minus 1. And we can do the same, so lambda 2 is equal to 4. So 2, 3, 2, 1, lambda 1, lambda 2 is equal to 4 lambda 1, 4 lambda 2. Multiply that out. Again, we have 2x1 plus 3x2, 2x1 plus x2 is equal to 4x1, 4x2, which implies that 2x1 plus 3x2 is equal to 4x1. Move that over, so this implies that minus 2x1, actually let's do it on the other side, so 3x2 is equal to 2x1, so x2 is equal to, actually divided by 3, so it's 2/3 x1, or actually we can just, we don't even have to go that far. So v2 is just equal to, well, 3 times x2. So let's say that's 2 and that's 3, and that will solve it as well. So then a homogeneous solution. So homogeneous solution. Well, it's just the solution is just x of t. Let's have the matrix x of t is equal to some constant, c1, times minus 1 to the t, times the eigenvector associated with that, plus c2 times 4 to the t, times the eigenvector associated with that one. And if we want, we can write this out as just a single vector instead of adding it as a sum. So then we have c1 minus 1 to the t plus 3c2 4 to the t, and c1 minus 1 to the t plus 1, since we have an extra minus 1 there, plus 2c2 4 to the t. And that is a general solution to this, to example 1.13. Furthermore, we can also say something about the spectral radius of the system. And so the spectral radius, rho of A, is equal to 4, because lambda 2 is equal to 4. And so that implies that, let's see, also, which implies that the limit as t goes to infinity of a to the t is not equal to 0. And of course we can interpret that, and if we look over here, well, that thing is not, if C2 is not equal to 0, then this thing diverges as t goes to infinity. So that gets bigger and bigger, or smaller and smaller. Or it's bigger and bigger either in the positive direction or in the negative direction. And I think that ends this expanded lecture into how you can convert higher order ordinary difference equations into systems of first order difference equations, and also I gave some examples on how to solve such problems, though I didn't go into full detail on how you get particular solution guesses. Those are a little bit troublesome, and I will probably not expect you to do too much of that. Well, thank you very much, and I'll see you in the next video.